Hello, everyone. Welcome. Can you hear me okay? Okay. My name is Srdja, and this is Joseph.
Yeah. Hello, everyone. Yeah, I'm Joseph. The two of us are from a company called Nordeus. It's a company stationed in Serbia, in Belgrade. Our company is actually doing mobile games, and we have two main titles currently, well, sort of on the market. The first of them is Top 11, one of our most popular, actually it's the most popular sports game on mobile in the world. It has more than 150 million users, registered users. And the other game is currently in soft launch in multiple countries. It's called Spellsouls. And yeah, the Spellsouls is the title that we are actually here to talk about. The two of us were mostly in charge of doing all the technical stuff on these titles. So basically writing shaders and fixing whenever something was not working. So yeah, let's dig into this. So first of all, we had, when doing this, when making this game, we had a few things that we wanted to achieve with this. So first of all, we wanted to aim for really high quality, like AAA graphics on mobile. By AAA, we don't mean like spending millions and millions of, or tens of, or hundreds of millions of dollars on the game, but on having a high quality game. So it should feel premium, should feel that it really has its effort put in it, and that it's made with a lot of love. And the other thing is that we wanted to support a wide range of devices, because a lot of people in some countries cannot afford like the newest devices, and we want to have a really widespread player base. So I'm guessing most of you don't really know what this game looks like. So we are just going to play a really short video that kind of shows you off how it looks like, maybe how it's played. So yeah, here it goes. Without the sound.
Unfortunately. Thank you.
The fight must begin.
Okay, so if some of you maybe recognize parts of the game, you maybe have noticed that this is the game that the assets were used for the demo on the keynote. So we used only the assets like the characters and the spells. Of course, they were a bit like up-resed and made a bit higher quality for the demo because it's a Titan XP after all on the demo, and this is a mobile device. Everything, the other game logic was written from scratch. So basically, the two games are not, I mean, they look similar. The camera is top-down, but that's all that there is. So yeah, this game is aiming to be a mobile MOBA. It's basically a clash of two spellcasters that cast a lot of spells at each other. So the spells have to look great, and well, everything has to look great. Let's just say it like that. Yeah, so we wanted to share the challenges of what we had like making the graphics and the performance of this game. So there are a few challenges that we had, and these are the things that we're going to talk about today. So first of all is our PBR shading. We call it PBR. We wanted to have a realistic dark art fantasy world. And when we say realistic, of course, the first thing that pops into mind is PBR shading. So we needed to somehow solve this to make it look real, of course. What we ended up doing is creating a lot of custom shaders, a lot of shader variants, and this became a problem very quickly. So we also had to address that. We're going to talk about that today. And no high-quality game is good if it is not running at 60 FPS. At first, we thought we were going to run at 30, and we were going to be happy about it. But when we saw that we could run actually 60, and when the designers and all the people in charge basically saw how it looks like running at 60, they were like, OK, no way, we're not going back to 30 FPS. And yes, this is for the highest end mobiles. And we need quality scaling to adjust for the low-end devices, which are, of course, not the same, like running on iPhone 4S is not the same as running on the newest iPhone 7 or 8. So yeah, I forgot to mention, so our lowest target device is actually a Samsung Galaxy S3, so on the Android side, so like Mali 400 range, and iPhone 4S. Okay, so first we're going to talk about the PBR shader, and Srdja is going to take over this part.
Thank you. Okay, so we wanted to have a very realistic game, and we also have multiple battlegrounds that you could see in the trailer, and they all have very differing lighting conditions. So PBR was the perfect fit for this, but unfortunately, as you are all probably aware, doing full PBR on mobile will simply bring the device to its knees. So we wanted to create a shader that looks 95 to 99% like PBR, but is much cheaper. And the first thing that defines PBR is the lighting model, how the things in the scene are lit. And usually when you're doing a PC game, it's a no-brainer. You're going to use the GGX lighting model because it looks the best, but it's also the most expensive. On mobile, you have to make some sacrifices, and since the screen is actually quite smaller than the monitor when you're playing a PC game, you can actually make sacrifices that are not so visible. And the first thing that we did is change the lighting model. So what we used is a normalized blink foam lighting model. I won't go into details of how it works, but you can Google it and you'll find all of the info. You can tweak it to make it look extremely similar to GGX while still being much cheaper. And the second thing that we always do when we're writing shaders, and not only the PBR shader, is to give our artists as much control as we can. Our artists are awesome, and they're very technical people as well, and they want to create cool stuff. And the more control we give them, the better stuff they can create. So in all of our shaders, we go with the principle that we call freedom for artists. So all of the things that make sense to be exposed so they can tweak it, we expose it. And we'll show you how the inspector for those shaders looks in 15-ish minutes, probably. It's a lot of stuff. So there are a lot of things that you need to do when you're writing a PBR shader. We won't go into the completely standard ones. We want to tell you what we did differently and what you can use in your games. So the first thing, this is one of our characters. It has a lot of different materials on it. It has some grayish skin, it has some cloth, some rubber, it has some lava, and it's all one material lit by PBR. This is the perfect example of a PBR use case. And we started by doing the completely standard roughness metalness approach. But when we ran that on mobile, we discovered that that's still kind of too expensive because you have to calculate a lot of stuff. And on mobile, you're probably going to be limited by the calculations and not by texture fetches. So we thought, OK, why don't we change it up a little bit? Why don't we remove some calculations and replace them by a texture fetch? So we did. We found out that the reflectivity part of the shader was very expensive to calculate, and it could be very simply put into our PBR control texture because we still had one channel available. So our PBR control texture is roughness, metalness, and reflectivity. Now, this is not pure physically based shading. It's not by all of the rules that you have to follow. But we're still making a fantasy game. And if you're making a fantasy game, it makes sense to allow artists to break PBR rules sometimes, because that way they can draw the eye to some details that they want it to be drawn to. And that's what we did by adding reflectivity as well. So they have more control. And yeah, that's pretty much it. And how we use these parameters. Roughness is completely standard. It describes how rough the surface is. Metalness simply describes if the reflection is colored by the albedo color. And reflectivity describes how much of a percentage of the CUBEMAP is reflected back to the user. You can see the channels of the PBR texture there. And this is a very good thing to remember. For mobiles, you really need to approximate a lot. And you can get away with a lot of stuff because the screen is so small. So now we have a character. It has PBR materials. So we need to put it into its environment because that's one of the most important things about PBR and one of the reasons why we used it. So for environment lighting, we use glossy environment CUBEMAPS. These are the standard CUBEMAPS that come with Unity when you check the glossy checkbox. They represent specular reflections of the environment. And this is an example CUBEMAP with different levels of roughness of one of our environments. The thing is, we really want the characters to pop on the screen. And as you can see, this CUBEMAP is kind of very grayish. So we wanted to emulate HDR, some parts of HDR, without actually using HDR, since that's too expensive for mobile still, at least the low-end ones. So what we did with these CUBEMAPS, we did something called HDR emulation or overburning. In the shader, we simply multiplied the red color values, and we get a much, much more vibrant texture with a much bigger color range. And it really makes the reflected things pop. This is all natively supported by Unity. You simply have to multiply it by the number you want. And we also made this controllable by objects so that the artist could make different objects pop differently. Next up is shadowing. So that's one of our scenes, one of our minions moving into shadows. We have two types of shadows, static light maps and dynamic shadows. Static light maps are cast by the environment, and dynamic shadows are cast by moving objects in the scene, pretty standard stuff. The cool thing about this is that we do blending, actually. And you can see how when the shadow goes into the light mapped area that they blend together. This is a really cool effect and something that if you don't have, will make the users notice very quickly. So, oh, I actually forgot this. So dynamic shadows are actually custom PCF shadows. PCF on mobiles is extremely cheap, and it makes the shadows look so much nicer, so I suggest you do it whenever you can. And the shadows can be combined. How exactly do we combine them? So we have a static light map. You can see that it's kind of bluish, so it has color information. It's really hard to calculate in the shader how much lighting an area is receiving when you also have color information. It can be done, but it's expensive. And since we had the alpha channel of the light map available, we actually, for each one of our scenes, render a static shadow map, which simply describes how much light every part of the scene is getting. And we use that static shadow map information to blend between dynamic and shadows and light maps. So you might be wondering how you can do this with Unity's Light Mapper, and unfortunately the answer is that you cannot. So that's all. So we used V-Ray to bake light maps outside of Unity, and it's not only because of this. This is a cool effect that we could achieve, but also we found that V-Ray light maps are actually much nicer, and they are much higher quality. So hopefully progressive light mapper will soon get in a state where it matches the quality of V-Ray, but it's still not there yet. Yeah. So, and finally, dynamic lighting. We have one standard directional light, completely standard. It's normalized Blim-Fong, but the focus in our game are spells. And we really want the spells to be very visible and to have very big impact, both visually and on the player. So we also added 4-point lights to our game. And these point lights are used exclusively by spells. The thing is that using standard way that Unity is currently doing lights, it's going to produce one draw call per every object that's being lit by a light. And that's no go on mobile because you really need to keep your draw calls low. So what we did, we wrote in our custom shader, we have one shader that can take 4 lights and light the object with all 4 lights at the same time. But since that's also kind of expensive for lower-end devices, we also created variants that take 2 lights, 1 light, and 0 lights. So drawing every object is still one draw call, but we can switch between these shader variants depending on the power of the device and how many lights are actually on the scene. And one really, really, really important thing that I need to stress if you're doing PBR, you really need to do your color calculations in linear color space. So the stuff with the lights and the linear color space will fortunately be solved as soon as the scriptable rendering pipeline is released, because it will automatically default to linear, and it's going to use a similar technique for drawing all of the lights at once. So if you're going to be using Unity next year, releasing on some version of Unity next year, you will have all of this built in. But if you're releasing now, you should really look into optimizing this. That's mostly it, what's special things we did with our PBR. We also wanted to share one tip that we found while writing all of these shaders, because we call it the best kept secret in Unity, because it's one sentence in a documentation file, not about this at all. and it's really cool. So the thing is that before, you had to write multiple shaders if you wanted, for example, one to be transparent, one non-transparent, or any other kind of thing like blending modes or stencil buffer or something like that. But now, you can actually expose those things in the inspector very easily. The code is there, but since we don't know if you can actually see it, we put a link in here that you can go to download an example shader that does this. We exposed all of these properties in all of our shaders. Artists actually even created some really cool VFX by changing blending modes to some values that make no sense but look really cool. And that's mostly it for our PBR shading, so I'll pass it back to Josef.
Yeah, so this was a lot of like theory how this shader can be written and what it actually looks like in the end. I just wanted to share a quick note how it actually happened writing this shader. So basically what I did is I have one sphere of Unity shader, have one sphere of soon to be a shader, and it's looking like, okay, let's move this slider, which is roughness, to the end. Okay, it becomes fuzzy. Okay, let's do that here. And we did that there. Then, like, okay, this is kind of a metalness. Let's move it to the end. Okay, this got some colors, like it's a red object, or the red colors popped out. That looks like a multiplication. Great, do that. And like a multiplication there, an addition there, and basically you stitch up a shader in the end. That is basically consists of a few components, and let's say modular, which actually we are going to take advantage in later stages. So basically, if you want to do something like this, just be creative, look how it looks like in the original form, and try to just translate it component by component to a new shader. It's going to end up being something good.
Yes, and actually magic numbers in shaders are good.
Yeah, a lot of magic numbers. Okay, yeah, let's continue. So the next thing is, as Srdja already mentioned, we ended up with quite a big shader. So this is only the inspector part. Like all these lines are a line in the inspector that is controllable by artist. So we're just scrolling down the shader file here. And you might notice that most of these can be like feature toggles, like toggles and enums. And this means a lot of multi-compiles, which translates to a lot of shader variants. So I'm just going to quickly explain what a shader variant is, just for the sake of consistency. Maybe you all know, but for those who don't. In Unity, you can define a shader to be compiled in multiple ways. For example, you can compile a shader to use a normal map and not use a normal map, for example. So you just define this, and what it actually happens internally, that Unity creates two shaders for you. Two variants, two codes, literally. One is that includes normal map, and one that does not. So we wanted to take advantage of this, because this way our shaders are way more cheaper, because of course if you don't want normal maps, you don't have to calculate it, and it's a convenient way. But yeah, problems soon arose. So we have two of these shaders actually. So these long shaders, one is for VFX and one is for PBR. So only two shaders used in the project. So we ended up with a lot of variants because as you saw, we had a lot of configurable features. And in the end, like back in the days, this was written like half a year ago or maybe a bit more. Like the keyword limit was 128, and we hit that no problem. And since that 128 is also like half of it is already used by Unity internally, and you cannot do anything about it. So actually, it's a bit less than 128. Nowadays, it's increased a bit to 256, but we still feel it's a temporary solution. And if we keep doing this, we're going to hit that limit as well. So that was a problem. Next thing is that our battle, so yeah, our game consists of like a menu part and a battle part. So when people want to battle another player, then they go into the battle part, and it takes some time to load the battle, of course. And it took like loading over a minute, because there are a lot of variants that needs to be loaded. And yeah, that's unacceptable, because the user will play a game that lasts for 3 or 4 minutes, and he's going to wait for a minute to enter the battle. That's unacceptable. So what do we do with this? So first we started observing. So we realized a few things. First thing, that certain multi-compile combinations are unnecessary. So let's say, for example, you have a multi-compile that controls how many lights you have in the object. So like 0, 1, 2, or 4. That's in our case. And you have another multi-compile that controls if if the lighting is going to be fragment shader lighting, vertex shader lighting, or no lighting at all. And this is exactly what we have in our case. So the artists have control over where the light is going to be, how high of a quality it's going to be. And you can realize that if you said that you don't want to have lighting on this, it's unnecessary to generate shaders that actually define shaders if it has 0, 2, or more lights. So we realized we could probably solve that. Also, we realized one more thing, is that we needed something in between a multi-compile and the shader feature. So yeah, I talked about there's a multi-compile, but there's also a shader feature in Unity that, of course, if you turn on this shader feature, then it's going to generate only the variant that you actually use, not both variants. So we needed something in between. Because we have a lot of features that are controlled by settings, and for example, normal map, again, I'm going to take normal map as an example, is we want to have it on high-end devices, but we want to turn it off on low-end devices. It would be meaningful to be a shader feature, but not all of the objects, it would be meaningful to be a multi-compile, sorry. But not all of the objects want to use normal maps. So you can leave it off on some objects, and you don't need to generate a normal map for that variant. So we actually need something in between. So to generate both variants when you actually use them, and only one if you don't use the other. So the end solution is we stopped using Unity variant system, and we made our own. This sounds maybe intimidating, but it's actually quite a simple solution. We have this system consists of two parts. First is a master shader. This master shader basically behaves as the Unity shader. So you write it, you put some shader, like multi-compiled shader features there. And after it, we process it and look at these shader features and look at our materials and decide what we need to generate. And we generate a bunch of variants. So we have basically a folder with a few thousand shaders that are actually the shaders that are used in the project. So yeah, that's basically how we solve the problem of variants. So we have physical Unity shaders in the project that are just going to be referenced by the materials, and our master shader that these shaders are generated from is forbidden to be used in the project, actually. So yeah, a few more tips that I wanted to share is shader compiling in the editor is slow. So this is either you write your variant system or not. This applies to everything. So when you include, for example, a Unity CG include, then it's going to parse that file, another file that it includes, and it takes a lot of time. So what we did is we just copied only the parts that we used from there. So like say luminance or maybe compression. And we put it in our own file and removed completely Unity CG include, and it increased the compile time of our shader in the editor like 10-fold or something like that. So yeah, be careful with that. If you have a lot of variants, it can take a lot of time. Yeah, I think that's actually what I wanted to say. So yeah, we're going to talk about performance now. So Srdja, you will take over. Oh, yeah, maybe one thing to mention is that out of all the include files, only HLSL support actually do not include other files. So it's OK to include that. But Unity CG you should avoid if you want fast compiling.
Yeah. I just wanted to add that Unity is actually very aware of this issue, so we're hoping for a solution to it soon. Last time we talked to them, they're thinking of doing something very similar to this, so hopefully soon keywords will be a thing of the past. Yeah. So, performance. OK, so whatever game you're making, you always need to optimize for frame rate, because if it runs at 5 frames per second, nobody's going to play it. But mobiles are much more specific than making games for PC. They're handheld devices, and you also need to be aware of other factors. So you also need to optimize for battery drain, and you also need to optimize for heating. It doesn't matter if your game runs at 60, if it drains the battery in less than an hour, that actually happened to us once before we started optimizing, or heats up so much that you cannot actually touch it. Also happened.
Yeah.
Yeah. And one thing that we always do, so there's a lot of philosophy of leaving optimization to the end. And we don't actually like that. We like to extend that philosophy. So it's OK to optimize the things that will make development slower at the end. But you should always know while you're developing how much performance you can gain and what you can optimize and keep things in a reasonable state. Because if you do not, you're going to end up with 2 weeks to launch and the game not running, and then you're just going to crunch for 4 weeks, probably. So Okay. One thing that I wanted to talk about is graphics profiling. I'm not going to tell you that you should do graphics profiling because you already know that. I just want to tell you how you can actually use some graphics profilers to your advantage. And one of the things that you actually do a lot is use the Adreno profiler. We also use Mali debugger, Snapdragon profiler, Xcode GPU profiler, but we actually prefer this one while we were developing Spellsouls. And the really cool thing is that you can actually view all of the shaders on your device, and you can actually change them in runtime. It takes like half a second. And building our game takes between 15 to 30 minutes. So if you want to change a shader, this is an obvious way to go if you're testing something or optimizing something. The problem with this is, I don't know if you can see it, but when you build your shaders to the device, the shaders are actually optimized, so they're almost unreadable. The cool thing is that you can actually tell the editor to compile your shaders into this format. You just select the shader and press the compile button, and then you just paste it in here and send it to the device, and you iterate in like half a second, like this. And this saved us weeks and weeks of development because you're never going to get it right the first time. Another thing that's really cool about these profilers is that you can see the total number of instructions for the shader, and we're going to get back to that in just a little bit. But for now, there are some performance traps that we saw a lot of developers falling into, and we also fell into when we were developing the first time. And the first one is that you should never measure FPS in development mode. This is kind of counterintuitive because you usually need development mode to measure FPS, but you should really use a frame rate counter and run it in production mode. The development mode is awesome for finding bottlenecks in your code, but the issue is that different parts of the engine get different amounts of overhead when you're activating development modes. You're never going to get the FPS that the user would get. So just use an FPS counter. And another thing, another problem that you can fall into or a trap is this. So, okay, this is about a frame rate graph of our game running for about 15 minutes. It was running our automated performance test. And one iteration of that test takes a minute. So this was running 15 of those. And you can see that the frame rate is extremely variable. The thing is that modern mobile devices, and even some older ones, are actually so powerful and have so little cooling that they can actually cook themselves to death. And the thing is that to prevent that, they actually drop their frequency when they reach the point of thermal saturation, so they can cool off a little bit. And that's exactly what happens in this graph. The game starts at 44 frames per second, and within 3 minutes, it drops to around 30, and then continues dropping down to 16 FPS. And if you want players to play your game for a long time, this will definitely happen to them. So when we optimize and measure performance for our games, the thing that we do is that we warm up the device first, so we get into that steady state at the end, so we can be sure that the performance will be stable there. And then we do our optimizations, and maybe turning off some graphical features to bring it to the target. And one thing that we do to prevent this from happening is that we actually, in this case, this device can't run 60, that's kind of obvious, and so we want to run it at 30. So what we actually do, we say 30 is our target, but we actually optimize our game to run at a much higher frame rate. We make it run at around 40 to 45 FPS. In the case of 60, make it run at 80, and then we cap the frame rate. That way you're never using all of the resources of the phone, and it's heating up much, much slower. And that's the final tip that we have about these performance traps. So you should always optimize for higher frame rate than the target that you set for that device. Okay. So shader instructions are how expensive your shader is. It's pretty much linear to the number of shader instructions it has and the area of the screen it takes. So this is kind of, or not kind of, it's completely obvious. You should always reduce your instruction count. But the non-obvious thing is that you should actually watch out for no-ops. You can see them in Adreno Profiler, for example. These are operations where the GPU is stalling for some reason, and they can usually be a symptom of a much larger problem. Some things that generate no-ops are, for example, ifs in a shader, modifying UVs in the fragment shader and then reading a texture from those UVs, Or maybe there are some other random reasons for knobs, which I'm going to show you later. So you should always watch out for them. Our shader, for example, has around 20 knobs, and that's about the number that we found is okay. But if you have more than 20, let's say 50, you should really check what's causing those knobs and try to reduce them, because you're almost certainly going to get better performance at no visual impact to your shader. So, okay. At one point, I was experimenting with GPU skinning. This is the standard matrix palette skinning technique that's implemented in the Vertex shader. It simply has some array of matrices for bone transformations and reads 2 of them and adds them together. It's extremely simple code. But when I ran this through the profiler, I noticed that there was something wrong, because this technique was running much slower than it should have been. And then I checked out what's happening and found out that this has 250 knobs. And our shader has 20, so there was something really, really wrong here. So I started playing around in the shader editor and moving some stuff around, not changing functionality at all, and came up with this. This is completely functionally identical, but this actually has 180 knobs. I don't know why, but the good thing is that this actually runs 20% faster. So the takeaway from this is that even if nothing is wrong with your shader, you should really run it through a profiler, try changing some stuff around. You might actually gain performance with no noticeable visual impact. And finally, you should always use half instead of full precision instructions. You can also see that in all graphical profilers. And half instructions run almost twice as fast than full precision instructions on most GPUs. The thing that you should also watch out for is converting between half and full precision, because that generates knobs and causes performance drops. So the thing that's also problematic here is that PC GPUs don't actually have half precision. So whatever you write in your shader is going to calculate with full precision. And that's really problematic, because then you cannot see artifacts that you have unless you build to the device. So what you actually do, we write the entire shader in half precision, unless we know for sure that some part needs full precision, so all of it is half. We push to the device, we see which parts have artifacts, and then in the shader editor, we directly on the device change the parts that need to be full precision to full precision. And that takes about half an hour to do for most shaders. But if you had to build every time that you needed to change some precision, you would be doing this for days. And just for a practical example, our shader has around 150 to 220 instructions, depending on the features active, and we found that's a good number to target if you want to have a very wide range of devices that your shader can run on. And these are micro-optimizations and require some effort, but there's an optimization that requires almost zero effort that's going to increase your performance a lot, and that's upscaling. The basis is this. Modern phones have extremely crazy resolutions, and most players cannot actually notice the difference if you actually render your game in a low resolution. For example, 1440p has 77% more pixels than 1080p, and when we tested that with actual users, they barely could see any difference, like less than 10% could see anything. So, but you can make your GPU run much, much faster if you render it 1080 instead of 1440p. And this technique can actually be activated very quickly. There are 2 types of it, hardware and software upscaling. Hardware upscaling means that you make your frame buffer much lower resolution, and you render into it. And then when the phone has to display the picture, it upscales it to the high resolution. This is much faster because the hardware is doing all of the work. But the problem is that if you have some UI, which needs to be extremely sharp, you might not be able to render it at low resolution. And that's when you should use software upscaling. That means that you render your 3D scene into render texture at low resolution, but you keep your frame buffer at maximum resolution. And then you upscale yourself into that frame buffer and render on top of the frame buffer your UI at full resolution. One problem that upscaling has, and why it's not used that common on PCs, is that it can actually produce a lot of jaggies. But the cool thing is that on mobile phones, due to their architecture, multi-sample anti-aliasing is basically free up to 4x. So you can just go into Unity quality settings, change that anti-aliasing to 4x, and you probably won't notice any performance difference. 8x has a little bit of performance impact, but you usually don't need 8x to make this look good. And for the final GPU tip, the biggest killer of performance on mobiles is overdraw. The thing with OverDraw is that mobile phones have very low fill rates. They cannot push a lot of pixels, especially if the fragment shader is expensive. And if you have a lot of transparent objects, you're going to be pushing a lot of pixels because all of them need to be rendered. There's nothing blocking the view. So you should be really careful about that. The problem with this is that your artists are not going to be aware of how much OverDraw is too much OverDraw. And there are a lot of situations when we were developing this game that artists called us to their PCs. They showed us Unity scene overdraw view, and it looked like this, and asked us, is this too much overdraw? And the thing is, we simply didn't know, because this is very abstract. You don't know what the colors are, and the human eye is really bad at averaging an entire picture. So for the first few months of development, we simply had to eyeball it, and it wasn't very good. But soon we figured out that it's actually possible to completely measure this overdraw in the editor and get an actual number that you can put in your budget so that the artists know what they have to do. And the cool thing is that you can do this using compute shaders in the editor. And we made that tool available on this link as well, so you can use it in your projects. Yeah? OK. So these were all of the GPU tips that we had for you. But if you want your game to run at 60 or even 30, GPU is not the only thing you have to worry about. You also have to worry about the CPU as well. And Joseph will tell you a little bit more about that.
OK. So there are a lot of optimizations, as you know, and you probably know about a lot of them. You maybe know about the things we are going to talk about now. But it's good always to remember these things. And let's go with the first thing. So preload and pull stuff. This is kind of obvious, so let's just repeat everything. So instantiating is expensive. You know, you all instantiated objects, and you know that it can have an impact on the frame rate. So basically, the frame rate looks like this, and this is absolutely not good because it's not a pleasant experience for the user if every once in a while the game spikes, and like it's running at 60, then it spikes for a few moments, then again running at 60, and again spikes. And yeah, so we need to fix this. And the first thing is, yeah, you need to do pooling. So pre-instantiate everything. Reuse objects. Basically, you instantiate all the game objects you need, you hide them after this, and you just show them to the user again when they're needed. But there are a few hidden tricks in Unity. So the first thing is you need to warm up your shaders beforehand. The thing is that you cannot be sure if the shader is loaded unless you actually render it. So what we actually do is during the loading screen, we render a small quad with the shaders we are going to use in that battle. And that ensures that they are actually compiled, and since they are rendered once, they will be ready to be shown to the user when they are needed. One additional small tip is if you're using Mechanim for animation, which probably most of you will use or would use, setting it to inactive and active again has its performance impact. So when you deactivate it, it simply deactivates. I'm not entirely sure how it's implemented, but when you reactivate it again, it will cause a spike because it's some initializing and guessing something with the serialization. So when we solved that problem by just disabling the renderers. So you just enable and disable the renderer, what actually the user sees, and this way the animators will not spike because they're staying in memory. Okay, so when you do these things, you get a silky-smooth FPS graph, which is what you ideally want. Next thing with what we did is we did view interpolation. This again might sound a bit intimidating because you need to reorganize maybe your code, but it's extremely good, and especially if you're doing a RTS style game, you should separate your game logic from your view logic. So in our case, we run our game logic at 20 FPS, and between showing the picture to the user, we just interpolate between them. So basically, what you need to interpolate is the position, and we interpolate position and animation. maybe there's something more, but I can't remember right now. But yeah, the goal is that you will get ticks and calculating game logic 3 times less often. So yeah, that's what we have. We have our view running at 60 FPS and our game logic running at 20 FPS. And also, this is really convenient for the networking part of the game. So if you do this, you can like get benefits in 2 parts of your game. So yeah, so what we do is just interpolate between 2 states. So it's good to remember. Might sound intimidating, but it's worth it in the end to do it. Okay, let's talk a bit about graphical scaling. So what we kind of found out is not every GPU reacts the same to every setting. So we didn't want to divide our devices into tiers. We could do it like it's a low-level tier, high-level tier, and stuff like that. But we decided to make every setting that we think it counts exposed. So basically, we have like normal max, reflections, shadows, anti-aliasing, render sizes, shadow sizes, everything. And what we do is we usually take a device and measure how it performs, and on the fly, we change the settings and see how the device reacts to it. We have the devices divided in few categories. So our quality settings works like this. So first, we check if there is a setting for that specific device. For example, iPhone 7. If you have settings for iPhone 7, that we're going to use that. Because we know we profiled it, it will work. If we don't have the settings for the device, then we will look on the GPU basis, because it's a pretty good indicator how this device will perform. Because like Adreno 306 performs kind of similarly across all the devices. And if we see that some device, based on the GPU setting, does not perform well, then we're going to take and make an exact setting for that device. And if we somehow miss the device, which can, of course, happen in the world of Android, because there's tons of Android devices, and we cannot possibly cover them all. There's some weird GPUs as well. We have a setting defined based on an API level. So we know that a Metal API will probably perform better than an OpenGL ES2. So we revert to that settings. Well, what I wanted to show is just a quick look how this looks in action. So I don't know if you can see there, I'm changing some settings, and it dynamically affects the device, and we get the FPS. So this is really fast because you can kind of warm up your device, and then it's warmed up. You have a tool that you can just click and change all the settings and see how it performs. And when it hits the target frame rate, or above the target frame rate, as we said, then we say we are done with the setting up of the settings, and we save those settings, and it's ready for the users. Something similar to this is Unity is already working on it. It's in early alpha, closed alpha, and it's called, how is it called again? LiveTune, yeah. So it's LiveTune. You will probably be able to get your hands on it soon, and this is the contact guy that you should contact if you're interested in something like this. So Angelo is your guy. Okay, so we are nearing the end of our talk. We wanted to recap just. So writing custom PBR shader pays off. It paid off in our case. We could have never done this with a generic solution that works on PC. Use GPU profilers. Use them to the fullest, which means like check the instruction counts, check the cycle counts, everything, and optimize little things, and they matter. Use your variants wisely. We wrote our variant shader system, but we would have never done that if we didn't have to. So maybe you could do a better organization to avoid this, because I would never recommend writing another system which you already have in Unity. So, and if you end up needing writing your own system, you can get some ideas of what we did to solve your problems. So use upscaling with MSAA. Of course, this is mentioned a lot, but it's always good to remember. So MSAA, as far as we know, is free. We never found a case when it's not, so use it, and it's way better to render at lower resolution because it's way faster. And of course, spool and preload. Don't forget about the shaders, and don't forget about the Unity animator that can give you some headaches when you're doing preloading. So yeah, that's it. Thank you for listening. Thank you for coming to our talk. And I'm guessing we have some time for some questions if there's any.
for the talk. Just had a quick question about the Angelo profiler you used. Does that work on all mobile GPUs, or does it specifically profile for the Angelo GPUs?
Adreno, yes. So only for Qualcomm GPUs.
Okay.
But for the others, you can use their specific profilers. Mali graphics debugger for Mali devices, Xcode GPU profiler for Metal and other Apple devices, and you can also use Snapdragon profiler for newer Qualcomm devices.
I think
How did that go on?
what I want to say is I think the Adreno profiler is broken for newer processors. So it's kind of old, but it was a really dear tool to us. Let's say it like that.
How do the other profilers compare to the Adreno?
The thing is, they all do slightly different things. So if you, for example, want to trace the API calls, Mali Graphics Debugger is much better. If you want to change shaders, then Adreno is your profiler. So you should try them all.
Thanks.
No problem.
Hello. How do you measure or count the knobs from the shaders?
How do we measure and count what?
The knobs,
knobs.
So Adreno profiler actually has a special category for knobs because they're such a big problem. Let me just find that slide. Okay, yeah. So this is standard shader view of Adreno profiler, and if you look at the bottom, there is actually count for knobs instructions.
Yeah. Just watch out for that, and it's easy to optimize.
Hi there.
Hey.
So you mentioned in the talk that you shouldn't measure FPS in development mode, and then you said to use an FPS counter. Which one did you guys use?
We write basically our own, so you can do whatever you like. But I think the best way that it works is just counting frames literally and updating it every second or whenever you decide it actually. So it's better because then there is no overhead actually, and you know what you're measuring, that it is actually what is happening.
Yeah.
Okay.
There's an implementation on Unity Answers, I think, which works pretty well.
Yeah.
What we did in the end, because we needed to measure multiple devices at once, we actually created a socket that sends data to our PCs, and that's how we got our graph that we showed.
Yeah.
Okay.
If you're doing a lot of stuff, it's worth it.
So you turned development mode off, wrote your own FPS
Yes,
thing, and that's
yes.
what you trust. Okay.
Yes.
Yeah.
Thank you.
Exactly. No problem.
Hey, good talk.
Thank you.
I was wondering if you guys, because you mentioned briefly about warming up your shaders with, rendering the quads.
Yeah.
We've used that trick before. I was wondering if you experimented with shader variant collections to do similar things, or like shader, warm up all shaders.
Yeah, we did. Warm up all shaders was problematic because we were only using a very small subset of shaders in every single battle, because we know which spells both users are using, so we can only warm up them. When we used warm up all shaders, it still took a minute to load, so we went shader by shader basis.
Yeah.
And back then, shader variant collections weren't working so well, so we avoided them.
And also it doesn't really agree with our shader variant system, so yeah.
Yeah,
We didn't
it
use
sounds like you kind of made that because the collections weren't really working that well at the time.
Yeah. I hear they're much better now, but we haven't tested them personally.
Okay,
Yeah.
thank you.
Okay, well, I guess if there are no more questions, then, we are going to be around here since the conference is ending, maybe for a few more minutes. If you catch us, then ask us whatever you think, whenever you want. And yeah, thank you for coming out to our talk, and see you around.